Hello and welcome to Aliathon's Universal Network Probe demonstration video. My name is Alan McDade and I'm responsible for sales and marketing here at Aliathon. The Universal Network Probe is a cost-effective and feature-rich solution for our customers in the network analytics and monitoring market space. The probe can be delivered to you in two different ways. The first is as FPGA IP for integration into your chosen hardware platform. The second is in partnership with Nallatech and is on demonstration here today. Nallatech's network processing cards are the perfect solution for customers who want a pre-verified, pre-tested network card for integration into their chassis. Furthermore, Nallatech's relationship with IBM and HP allows us to offer a one-stop shop server platform with the card and IP pre-installed. This helps our customers to accelerate their time to market and offers a singular warranty for the entire platform. Now, before I take you through the demonstration, I'll first walk you through the hardware setup and the FPGA architecture. The diagram on your screen now shows the hardware setup for our demo. The client signals are generated by the JDSU tester, which for this demo is configured to provide OTU 2E and 1E containing a synthetic 10 gigabit Ethernet client signal, as well as native LAN PHY or 10 gigabit E. The tester has an XFP optical module installed, which is connected to the SFP Plus module in the hardware chassis via a single mode optical fiber. The chassis being used is an IBM System X 3650 M4 server, which in turn has the Nallatech 287n network processing card installed in one of its PCIe slots. Aliathon's Universal Network Probe resides in one of the two Xilinx Kintex 7 325T FPGAs on the Nallatech card. At this point, we begin our transition to the software domain via the PCIe bus, which is managed by Nallatech's controllers and drivers. For this demo, we are using some freely available software tools to capture and analyze the incoming packets. Our low-level driver and network layer libraries are provided by WinPCAP, which is an industry-standard link layer access platform for Windows. The application software sitting on top of WinPCAP is provided by Wireshark, a free and open-source packet analyzer. Finally, Aliathon statistics interface, which includes the transport layer errors and defects, is reported to the user over the PCIe bus via a terminal interface. The diagram on your screen now shows the top-level architecture of Aliathon's Universal Probe design that resides in one of the Xilinx Kintex 7 FPGAs on the Nallatech network processing card. The design can be configured to have as many Universal Probe line interfaces, or UPLIs, as is required for the application and/or can be supported by the target FPGA. Each client is deframed and demapped by the UPLI in accordance with the relevant standard, irrespective of its rate relationship with the transport container. These relationships can be constant bit rates or asynchronous signals requiring transmission convergence. Demapping techniques employed are the asynchronous mapping procedure, or AMP, the bit synchronous mapping procedure, BMP, and the generic mapping procedure, GMP. Each UPLI feeds to the memory management unit, which is configured to buffer the data in the granularity required by the upstream system. For simplicity, today's demo has been configured to use only one of these ports. The host interface delivers the raw data and line health info to the upstream processing unit. Statistics, errors, and defects are provided for all protocols and all layers of the design via Aliathon's configurable microprocessor link. Each UPLI is individually configured with the protocol mappings of choice, as is shown in the diagram that is now on your screen. In 10G mode, the UPLI can be configured as follows. For Sonnet SDH, it can be native OC192 STM64 for proprietary SDH structures. It can be OC192 STM64 carrying 10 gigabit E or Wi-Fi Ethernet transport. It can be OC192 STM64 with a POS layer, which is for packet or legacy packet transport. And finally, for OC192 STM64, it can be GFP packet or modern packet transport. For Ethernet, this is native 10 gigabit E or LAN-Fi. For OTN, it can be native OTU2, 2E, 1E, 2F or 1F, or any other proprietary OTU 2K structure. It can be OTU2, which is carrying OC192 STM64 for legacy TDM transport. It can be OTU2, which is carrying OC192 STM64, which in turn has 10 gigabit E in the payload for SDH packet transport extension. It can be OTU2 with GFP mapped packets for legacy packet transport. It can be OTU2E or 1E with 10 gigabit E carried for modern Ethernet transport. And finally, it can be OTU2F or 1F, which is carrying fiber channel, which is the modern fiber channel transport. Although not demonstrated in today's video, the design can also be configured to support sub-10G protocols for line rates such as OTN, OTU1, for Sonnet SDH, OC3, STM1, OC12, STM4, or OC48, STM60. Finally, the design can also support sub-rate Ethernet at the 10, 100, and 1000 base T rates. Okay, let's move on now with our demonstration. The data paths chosen for today's demonstration are OTU2E and 1E, both carrying a synthetic 10 gig E client signal, and also a 10 gig Ethernet or LAN-Fi signal. So we'll start with OTU2E carrying 10 gig Ethernet. So we'll first configure our JDSU tester. So we can see here it's configured for OTN carrying LAN traffic. The PHYs are configured to the OTU2E rate. The OTN transport layer we'll come back to in a second. And at the MAC IP layer, we can set up our traffic. So if we set this initially to IPv4, and we'll leave the protocol as TCP, we can then set up our traffic to 100 megabits per second, and the traffic profile with a random frame size. The reason that we're setting our bandwidth to 100 megabits per second is purely for demonstration purposes only. The design on the FPGA can capture everything at wire speed. However, the Wireshark application layer, which is software based, would really struggle to process 10 gigabits worth of frames in a reasonable time for a demonstration video. So we'll leave that at 100 meg, and that's our traffic setup. Before we look at the packets in Wireshark, if I go to the terminal, and we can examine the transport layer. So for example, if I go to OTN and alarms and errors, I can do things like stress the FEC and watch as that's reported at our transport layer. I can also insert an SMBEI, and again watch as that's reported back in the Aliathon terminal. We can also, if we send some traffic, error things like the FCS. So at the bottom of the screen here we have a MAC IP layer report, and if I turn on some traffic, we can watch as our FCS counter accumulates. Now if I launch the Wireshark application, and we'll start a new capture, we can send some traffic to the application layer. Okay, and if we examine a few of these packets, so we can see first of all, if we look at one or two, that the number of bytes in the frame changes. And then if we take any frame at random, we can see that the Internet Protocol is version 4, the protocol is TCP, and that the frame check sequence, the FCS, is incorrect, which reflects the alarm setup in the JDSU. We can also see that there's a timestamp associated with each frame to emulate a real customer system. We've added a timestamping function into the FPGA design. So this allows us to help Wireshark capture the actual time for each of the frames as they came into the system. If I stop that capture and then go back to the JDSU and slightly change the frame format, so take the FCS errors off, go to our flow, set that to IPv6, change to UDP, we'll leave it on random frame sizes. And then transmit some traffic to the application layer. This time we can examine these captured packets. Again, a different number of bytes per frame. We can see that the IPv6 is now in place, and that it's the UDP protocol being used. Okay, so we'll now switch to OTU 1E. To do this, we reconfigure the PHYs in the JDSU to 1E, which slightly slows down the data rate to the 1E rate. We then go into our FPGA design. And via the terminal, we can reconfigure the FPGA SerDes to the new rate. Okay, again, if we start with our JDSU, and again, we can examine the OTN layers, so we can, again, like last time, we can inject some errors and watch those reflected in the terminal. We can send some traffic with errors and watch as that's reflected in the terminal. And then finally, if we go to our Wireshark application, we can capture some packets for analysis. So again, here we have IPv6 frames. We have a correct frame check sequence, sorry, an incorrect frame check sequence, and the UDP protocol being used, which is matching the setup in our JDSU. So now we'll switch to LAN-Fi. So to do this, we reconfigure the JDSU to 10 gig E. This takes about a minute to reconfigure. And what's actually going on here is the JDSU tester is reconfiguring the FPGAs on board to the new 10 gig E LAN-Fi rate. So while that's configuring, we'll go in and we will configure the SerDes of the FPGA to the LAN-Fi rate. Okay, and that's complete. And if we wait a second for the JDSU to catch up. Okay, so this time we have just vanilla flavored LAN-Fi on the tester side. Again, we can go in and set up the frames and packets. So this time we'll leave that IPv4, perhaps switch to TCP protocol. Again, set our traffic to 100 meg. And leave our frame sizes at random. Okay. Again, we can examine the transport layer in Aliathon's terminal. So again, if we send some traffic to the Wireshark application. Sorry, to the terminal. We can again perhaps add some FCS errors. And then watch as those are counted through the Aliathon terminal. Okay, if we launch a new capture now in Wireshark and send some traffic from the JDSU. We can see those captured packets. So again, random frame sizes. The protocol is TCP, version 4, and this time the frame check sequence is correct. We can change that again on the JDSU side. We can, this time, perhaps insert some FCS errors. We can change to fixed packet sizes. And IPv6 UDP. Again, set up Wireshark for capture. And then send some traffic. Okay, so this time we can see that we have a consistent frame size, in this case 266 bytes. We can see in each of those frames that the Internet Protocol version 6, we can see that the frame check sequence is incorrect and that the protocol is UDP. That concludes our demonstration. That's the end of our demonstration video today. I hope you found it useful. For more information on the Universal Network Probe or any other Aliathon products, please go to our website, www.aliathon.com. To contact us and discuss your project requirements, please go to aliathon.com and click the Contact Us tab at the top of the page. Thanks for watching.